Alright, 8, 9. It's been a while since we've done 9 sections in a chapter, but this one's so cool you're not even going to be able to believe it. Okay, it's about binomial probabilities. I mean, come on. That sounds like a party right there. Alright, after the watching the video, you should be able to talk about this stuff. Now realize we have a quiz before this one. There's a quiz on... Oh, there's a quiz on the 18th, and after the quiz we'll be able to talk about 8, 9. These are the questions you're going to have to answer, so have a look at that. Okay. So what are binomial probabilities? Binomial experiments are experiments that have two outcomes. Things like tossing a coin. Things like in medicine, did the person get cured or not? Success, failure, basically is what we're talking about. And you can compute these probabilities if they're uneven using the binomial expansion, using the Pascal's triangle kind of stuff that we've been working with. So it's actually kind of cool. Alright, so remember the thing we did with the 3 coins. If you make an experiment that has tossing 3 coins, we can think about all the ways that can possibly come out. Heads, heads, heads. Heads, heads, tails. We've done this before. Pause for time. Bang. Okay, and you see that there's 8 different possibilities for that. We could sort these, kind of like we used to sort stuff like sum on dice and that kind of stuff. We could sort this into a variable we care about, like number of heads. Now this is a pretty simple example. We're going to get this, we're going to expand this to be about more stuff in a minute. But the number of heads you could possibly get on these things is 0, 1, 2, or 3. For 0 heads, well, I guess that would be this one right here. There's one way to get 0 heads. 1 heads, okay, so I'm not talking about that one right now. 1 heads, I guess that would be this one, or this one, or this one. There are 3 ways to do that. Okay, so I've counted those. And 2 heads, there's 2 there, 2 there, and 2 there. There's 3 ways to do that. Okay, I've counted those, so now there's only 1 possibility left for the 3 heads, and that's what it is. Okay, and that's good because there's a total of 8 outcomes. Good, those are the 8 outcomes, and I've just sort of sorted them into how many ways are to get that many number of heads. So if everything was completely fair, and this is what we did back in the days of probability, you could say, what's a probability you're going to get exactly 0 heads? Probability 0 heads is 1 out of 8, and that kind of thing. Probability of 1 heads, exactly 1 head. So there's 3 ways out of 8 that can totally happen, and so on. You also might notice these little guys right here, the 1, 3, 3, 1, was part of Pascal's triangle. This is not a coincidence. 1, 3, 3, 1 came from, is this little part of the table. This also means that if we were going to take, our book does x plus y, and take it to the guess what power, third, because we're flipping 3 coins, that this would equal x cubed plus 3, and the coefficient there is 1, 3 x squared y plus 3 xy squared plus y cubed. You see any similarity here between that kind of thing and this kind of thing? I mean, this was about basically 3 tails. This is kind of like two tails and 1 head, and kind of like 1 head and 2 tails, or sorry, 1 tail and 2 heads, and kind of like 3 heads. Yeah, and these probabilities can factor out this way. Now, if everything is 50%, this is not very interesting, and I can just say these are regular old fractions out of 8, because everything is equally likely in heads and tails. But when we start talking about success and failure, I have the same thing, success, 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 all the way down to failure, failure, failure. I'm going to have those same 8 outcomes. But if I want to know the probability, say, of 2 successes, exactly 2 successes. And let's say I know that on any one trial, I need to know this. The probability, if we're talking about one trial, if I know the probability that S is going to be successful is, I don't know, let's make it interesting. Let's make it 25%. The example in the notes is 30%. Let's say it's 25% success rate, which is really bad. I don't know. Say we're talking about, I don't know, getting selected for a certain college or something like that, and your probability is of an SAS graduate going to this college is generally 1 out of 4. So just from that information, we have enough to be able to compute this now. I'll change colors to the answer mode. Because right now, if I really wanted to know this, I could know, well, what's the probability that you fail that college application thing? Well, on one trial. Well, if your success opportunity is 25%, the probability you fail getting in is probably 75%. Let's say we have 3 students applying to this college. And we want to know what's the probability that exactly 2 of them are going to get in. This is how we do that. We would find that place. You know, the whole distribution of that is, let's call them. The book calls these P and Q. I don't really like this. I'm going to call this X and Y, like we did before. X and Y in the binomial expansion. The probability, all the probabilities of all those things happening is going to be like this again. It's the binomial expansion of X plus Y cubed. Okay, so the part I really care about is 2 successes. 2 successes is when X happens twice and Y happens once, which is this one here. So I want to know, it's going to be 3 times 0.25 squared times the possibility that it fails. Another way, and I could actually do that on the calculator. All right, on the calculator, that's, whoops, not plus, times 0.75. Okay. It's, whoa, wait a second. Oh, I have 3. Oh, come on. Sorry, everybody. 3 times 0.25 squared times 0.75. See, now these calculators are very expensive and very, you know, trustworthy most of the time. You get an answer like that, that should automatically make you say, whoa, I did something wrong. I got a probability that's greater than 1. That ain't supposed to happen. It's supposed to be 14.0625%. Remember all those digits? 625. Yeah, okay. So there's roughly a 14% chance that that's going to happen. Exactly 2. Now, a lot of times they ask you stuff like, more interesting question is, what's the probability that we have at least 2 successes? And that's a little bit more difficult because in order to have at least 2 successes, that's like saying the probability of exactly 2 or means plus, the possibility that there could be 3. So I would have to find that thing also, but then I'd also want to add on to it the probability that there's 3. The probability that there's 3 is actually right here. Success would have to happen all 3 times. That's actually kind of easy to think about, I think. Probability that all 3 are successful is 1/4 to the 3rd power, which is, I should be able to do that in my head. I can't. What? Pushing buttons too fast. To the 3rd power. Didn't I push 3? Okay. 0.015625. 0.015625. And it's amazing how often that you have these crazy decimals, and they look crazy on their own, but you add 2 of them, and all of a sudden it turns out to be something nice. Let's try to add those together. That plus 0.14. 0.14065, was that right? I think it was. These 2 added just something a little bit smaller. It's like exactly 10 times that. Now, would you have expected that? I don't know. P2 or 3 is exactly 10 times P3. I don't know if I would have guessed that. Anyway, that's how you do that. And now you're looking at this going, okay, between this one and this one, that only adds up to 15%. Well, yeah, if I keep adding these things, if I actually calculated that one and that one, this whole string of things with all these probabilities in here, this will always add up to 1. If you think about it, that came from that whole thing actually equals, remember, x plus y cubed. And what is x plus y cubed, really, in the grand scheme of things? X plus y is 1. I cube it, it should be 1. So individually, these 4 little things are kind of crazy, but they will all exactly add up to 1. It's kind of cool that way. Okay, let's get a little bit crazier. Let's say we have some experiment or something where the probability of success, if I can draw, how come I can't draw all of a sudden? Just a second. Okay, let's say we have this experiment where it's about, because I'll relate to a story some kid just told me, that any random day when you take a taxi to school, let's say the probability that you get to school safely, I'm going to make it kind of low just because it'll make it an easier problem to deal with, but this is kind of crazy. Let's say on any random day, the problem that you get to school safely is going to be 98%. Oh, 97 makes it a little more. I mean, that's a horrible percentage, actually, if you think about it. Only 97 out of 100 days do you get to school safely. That means 3 times something happens. Because this girl had something happen to her on the way to school is really a strange probability. Her taxi broke down. Okay, so, or at least that's what she told me. Maybe she just didn't study for her test. Anyway, getting to school safely or probability of failing that. So, accident, breakdown, etc. So basically failing the first thing. We have a binomial situation. I'll even say etc. Basically failing the first thing. So the probability of any kind of failure is going to be the rest. So in situations only like this is what we would call binomial probability, where we have two things that have to be basically mutually exclusive and independent and complementary and all that stuff. There's only two possibilities and they add up to one, and they are independent. Okay, so then we're going to talk about what's the probability, because I want to do a really crazy one. What's the probability you get to school safely all year? Probability of, and there's how many school days in a year? Let's say 180. Success, or getting to school safely. Exactly. Actually, you know what? That's kind of silly. Let's say 180 would be too easy. Let's say I want to make a harder problem. Let's say exactly. Because the 180, you would just take this to the 180th power. That's not what this is about. Let's say exactly. What's the probability that you do exactly? And I don't want to pick one that's kind of in the middle of the chart here. Exactly 175 safe trips. Now that's really weird. Maybe I should type this. It'd be faster. I don't know. We should be able to read it better. Okay. What's the probability of exactly 175 out of 180? You need to know how many trials there are, too. That's also one requirement of the binomial distribution. You have to know, when you're doing this, you got to know how many powers are we taking this to. We got to know that this is a 180. So what we're looking for here is really in that whole grand expansion, x plus y to the 180th power, which by the way would take all day to write out. It's going to start with x to the 180th plus some combination times x to the 179th y plus, actually I'm going to get there pretty soon, right? The one I care about is some combination x to the 175th y to the 5th plus blah blah blah. I mean, this expansion is huge. It's got 181 terms in it. It's the 180th row of Pascal's triangle. The term I care about is this one right here. And I guess the hard part is trying to figure out what this combination is. This combination, if you remember from the binomial expansion, well, it's out of 180 things, how many am I choosing to be successful? Or you could think of it this way. The number on the bottom here is also the same as, this is the 0th one, this is the first one. It's kind of the same as the exponent on y. So I'm really choosing 5 things here. If I did 180C, basically 180C5 is the same as 180C 175. So actually you could do either one. You could do either exponent. It should be fine. Okay, 180C5. When I figured that out, then I'll take it times these two things, times x, which is the success rate. Think about this. This ought to happen most of the time, right? 175 times that has to happen. And 5 times this is supposed to happen if it's exactly. I mean, that's too bad. This person got in 5 accidents or something. But I just sort of made this up. This is horrible probabilities. Don't tell your parents. I'm hoping that you have an accident on the way to school, or you should use it as an excuse more often. Anyway, this is it. I'll figure this out in the calculator. 180C5 is probably a pretty big number, actually. 180 math probability 3. Now, how come I didn't get my 0? Come on. 180 NCR 5, which is a huge number. But then this probability is going to reduce this so much that when I multiply it by these last couple things, this becomes less than 1. Times, do I want to write this down? I really don't. Times 0.97 to the power of 175 which is probably going to make it smaller, but not a whole lot smaller. I mean, this is really close to 1, right? Oh no, it reduces really fast. Anyway, it's still pretty huge. And then I got to take that, then times 0.03 to the 5th power times